So we are on the journey to figure out how we can get the area underneath a curve. And we've started by breaking up the area into rectangles. We're looking for this area under this curve. This is 17 minus x squared. And we want to approximate it with rectangles that just touch the curve in one point. Well, if we had one rectangle, that's a pretty bad estimation, all right? We could do the right-hand rectangle. There it is. We could do the left-hand rectangle. That would be an overestimate there. We could choose the midpoint. But one rectangle sure doesn't do us very good there, all right? Well, what if we bump that up a little bit? Let's go somewhere in between there. Okay, 5 rectangles. There it is. Well, when we do 5 rectangles, we get pretty close, okay? All right, and so here we got an overestimate with the left hand. The right hand is an underestimate, but we still we're off by a little bit. And we can see here's the sums for 5 rectangles. The right-hand sum is 39-ish. Left hand is 52. That's too high. Midpoint is somewhere in the middle. That's nice. So probably close to that midpoint. And we've seen, what happens as we get more and more and more. Now, it's hard to see, but there are some little spaces still in there. Let's dial it back a little bit so we can kind of see the spaces. The resolution on the computer is kind of limiting to us here. All right, here we have 19 rectangles, and we can see there's still a little gap there, right? With 19 rectangles, we're getting a little closer here. The right-hand sum is 44, left-hand 48, midpoint 46, okay? And then if we crank this up, and here's where this will tax your computer a little bit because it's drawing a lot of rectangles and doing a lot of calculations. We'll see if we can, there we go. If we get this over to 500 rectangles, well, they're still not the same. It's 46.6, 46.7 for the left hand, and the midpoint, which is probably pretty darn close, is 46.6. Now, if we went up to 1,000 million, trillion, billion rectangles, these would all be pretty much the same. It wouldn't matter if we're using right hand or left hand or midpoint. So, as we do this, what we want to do is we're going to use summations now, and it doesn't matter which rectangle we're going to use, so we'll think about the right-hand rectangles. And so we're going to find that exact area, okay? So we want to consider this. What happens when we take and we move from 100 rectangles or maybe 10,000 rectangles, and as we go to infinity, we call this a definite integral of this function from 0 to 4, all right? So this is our definition of a definite integral. So here's how we compute this, all right? So let's make a summation function to find, and we'll call it S of n, to find the lower sum or the left-hand sum. The lower sum is another name because it's below, all right? So we'll think of, the right-hand sum in this case. Right-hand sum is the one that's below, all right? And so let's do that, okay? So we've got we're going to sum up the rectangles, okay? And we're going to go from n equals 1, or let's actually make that I equals 1 to n, okay? And we got to think about each rectangle. Think about just one of these rectangles, okay? Maybe it might be helpful to think of the first rectangle, okay? Well, we've got a length times width we got to think about, okay? All right. And so we have n rectangles or n subintervals. So the whole thing is 4. So how wide is one of them? Well, we're going to take that width of 4 and we're going to divide it by n. Well, how big is n? It might be 100 for 100 rectangles or 10,000, all right? We'll pick that in a few minutes. Right now we'll just leave it variable. So we're going to take the width, so there's our width, and we're going to multiply that by the height. What's the height of this first rectangle? Well, the height of this first rectangle is f of, whatever this is, f of, well, the first x value there the first x value here is going to be 4 divided by n. Okay? So 4 divided by n would be that. Now the second x value, what would this next rectangle be? Okay, that second x value there, okay, would be, well, twice as far, right? Because 4 divided by n is the width of one of these rectangles. The width of the next one would be 2 times that. Well, 2 times 4 divided by n, well, let's just do it as 4 over n times 2. All right, well, where's the next one? The next one over here is another gap. All these gaps are the same. So this next one right here would be 4 divided by n times 3. So we have 4 divided by n times 1, 4 divided by n times 2, 4 divided by n times 3. So if we were to add all these rectangles up and to write it all out, the first rectangle would be 4m divided by n, and we're going to multiply that times f of 4 over n times 1. Well, what's the next one going to be? It's going to be the same width, 4 divided by n, times f of 4 divided by n times 2, because we're going over 2 4/nths, okay? And then we'll continue that on. Well, notice what's changing here. The 1 is changing, the 2 is changing, so on and so forth. So we're going to have the height of this is going to be, we got the width already, okay, times the height, or the length if you want, to turn it on its side kind of. Okay, the height of the rectangle is going to be f of 4 over n times 1 times 2 times 3 times 4. Well, that's our counter. 1 times 2 times 3, so times I. And there it is. So each pair, this pair represents the area of one rectangle. And how many rectangles are we going to have? We're going to have n. And so there we have it. All right. That is our expression here. Okay. Now, what if we have 100 rectangles? Well, we're going to actually have to take that one step further here. And for this function that we're talking about, okay, let's make it specific here. All right. So we have, this is going to be for 17 minus x squared. So we're going to have the sum from 1 to n of 4 over n. Okay. Now, by the way, n is a constant. We're going to pick it. N is not changing. This is not changing. So we can actually factor that out, right? That doesn't actually need to be in the sum there, all right? But we will eventually here. Let's leave it in for the moment. So 4 over n times 17 minus, and we have x squared, so x is 4 over n times I squared. All right, there we have it. Okay, so now we want to evaluate that. And we want to find the approximation. Let's use that for n equals 100. Okay, there's our function. So we have the sum of I equals 1 to n of 1 to 100, right? 1 to 100 of 4 over 100 times 17 minus 4 over 100 times I squared. Okay? So there's our width times the length. Okay? All right, using our TI Inspire, let's use that. All right, I from 1 to 100, 4 over 100 times 17 minus 4 over 100 times I squared. By the way, that needs to all be in parentheses inside the sum there. We get 46.3456, okay? 46.346, we'll round that off, all right? 46.346. 0.346. All right, well, what if we did 1,000? Okay, so this would be the sum of, same thing here, so let's go in blue here. The sum of I equals 1 to 1,000, and 4 over 1,000 times 17 minus 4 over 1,000 I squared. All right, that whole thing is going to need to be in parentheses. Let's check it out on TI Inspired. And that's going to give us, looks like 46.63, so it's changing a little bit, 635. 46.635, all right. Now, we want to know, well, what happens? That was 10,000. What happens if n goes to a million, billion, or n goes to infinity? Well, let's work that one out here. So we got to go back to our expression with n, and that's I equals 1 to n. N is the number of rectangles. And we had 4 over n times what do we have? We had f of, which was 17 minus 4 over n times I squared. Okay? All right. So let's simplify this, and then we're going to find a limit. Okay? What is this getting close to? And this is where calculus will come in, the concept of limits. Now, this is a constant. N is a constant. It's 1, then it's 10, then it's 100, then it's 1,000, it's million. But, okay, so when we start talking limits, yeah, we're imagining it growing, but at any moment in time, this is constant. I is the thing that's changing, okay? So we can bring that out here. 4 over n. That is not changing, all right? So you pick an n, and then that's fixed for the moment. Okay. Then let's clean this up inside. We have 17 minus, and let's make that 16 over n squared times I squared. All right. Now, we can clean this up. Well, we can evaluate, I should say, by getting taking the sum of both of these here, right? So we've seen that this is going to be equal to the sum of I equals 1 to n of 17 minus the sum of I equals 1 to n of 16 over n squared I squared. Okay. Now, again, this right here is, in terms of n, that can be brought out. Okay. I know this gets a little complex here, but let's do that. Let's bring out the 16 over n squared times the sum of I equals 1 to the n I squared. Okay. And we'll copy this down and we'll evaluate this next. All right. Now, we have ways that we've developed to evaluate these summations. So first one we have here is we have the sum of a constant. So this is 17 plus 17 plus 17 plus 17 plus 17 n times. What does that come out to be? Well, that is 17 times n, right? All right, so that part became 17n. Then we have 16 over n squared. We want everything in terms of n here, okay? And so let's think about this part here, okay? The sum of I squared. Well, remember we developed some formulas in the last lesson there, okay? So this is one we want to memorize. All right, I squared gives us n times n plus 1 times 2n plus 1 all over 6. Okay. We're going to need to find the limit here in just a second. So let's clean that up just a little bit more, and then we'll talk limits here. All right. So let's go. I'm going to copy that down here so we can work with it. So let's keep going with this here. We want to clean it up because we're going to need to find the limit. So let's distribute this here, and at the same time we'll make one fraction here. So we got 4 over n times 17n. Well, those n's are going to cancel here. Okay, these n's will cancel. 4 times 17 gives us 68. Okay. Now we're going to put this together here. Let's actually cancel one of these. Cancel that in with one of these. That works good. All right. Let's cancel here. Make this 3. Make this 8. All right. And then we're going to let's go ahead and take this 4 over n times what we have left there. And we got 4 times 8 on top. That's 32. And we have n plus 1 times 2n plus 1 all over. On the bottom we have n times 3, and that's going to be 3n squared. All right? Well, I think we're ready to find a limit. So that is an expression for the area. All right? So we've got an expression for the area in terms of n, the number of rectangles. Notice there's no more summation, so that's our first goal, is to find the area is equal to this, all right? And so now we need to find we want to take the limit of that, okay? So actually we should say this, this is an area approximation, but to find the exact area is when we have infinite rectangles. So the exact area here is the limit as n goes to infinity of 68 minus that whole thing there, which, let me go ahead and do a little more work because this will be helpful here. We're going to, let's multiply this out. Okay, we distribute that stuff, and it comes out to be 2n squared plus 3n plus 1. Okay, we're getting close. We're almost there. A lot of algebra going on. Okay, and we're about ready to take our limit. Okay, now this is a summation. Okay, as n goes to infinity, well, that's going to stay 68. All right, let me distribute this 32. And we get 64 n squared plus 96n plus 32. Now, what's happening here? We got to remember how to do limits. It's been a while. Go way back to the beginning of the year. As n goes to infinity, 68 is equal to 68. As n goes to infinity, in this fraction, remember we have some leading terms of n squared and n squared. So these are small potatoes in relation to a million squared or a billion squared. Okay, so we can ignore, because we're going to the infinity, we can ignore the lower degree terms. And once we do that, we have 64n squared over 3n squared. Well, those n squareds cancel. And now we're left with 64 thirds. So minus 64 thirds. So we just found our limit. Now we just compute this. Getting a common denominator, 204 thirds over 64 thirds. 204 minus 64 gives us, what, 140 thirds? Which comes out to be 46 point, well, let's say make it exact here. No points. 46 and 2/3, which is 0.6 repeating. And what do you know? That looks a whole lot like what we were getting here. 46 and 0.666 is what we were headed towards. There's our exact area. Okay, so that's the process. All right. So we found the exact area, finding or using limits. All right. So once again, what's going on is this. We write our expression as a summation here. And then we're going to take that expression and we're going to work with it using our summation properties. And we'll find the limit as the number of rectangles goes to infinity. And there we're using our limit properties. All right? So there you have it. It takes some practice. And with practice there, we can find the exact area under a curve like this. Keep it up. We'll see you soon.